Today, we're going to trace the very core of modern manufacturing. We're talking about a journey from a tangled mess of wires to the super smart processors that run pretty much every factory you can think of. We're going to explore the revolution that made modern automation what it is today.
Have you ever just stopped and wondered how a modern factory can churn out thousands of products an hour, each one absolutely perfect? You know, how a car is put together by robots with flawless precision? Well, the answer isn't just about the machines themselves, it's about the intelligence that controls those machines. And that's exactly what we're diving into.
So at the heart of all this is a concept called industrial automation. Really, all this means is using control systems, like computers and robots, to manage all the machinery and processes in a factory, with as little human help as possible. Think of it as the invisible brain that's orchestrating all the muscle on the factory floor. It's all about achieving perfect consistency and efficiency.
So why is every single industry scrambling to automate everything they can? Well, the reasons are pretty simple, and they're huge. First, automation slashes human error, which means better quality products. It also drives down costs in the long run. And, maybe most importantly, it makes factories way safer by taking people out of dangerous jobs. Better quality, lower costs, and more safety for any engineer or business, that's a total no-brainer.
But you know, to really appreciate how sleek modern systems are, we have to go back in time. We got to look at where this all started. Before the digital age, control panels were literally a physical maze of wires and these little clicky switches called relays. Every single decision a machine made had to be physically wired into place.
And this little guy was the building block of that whole system, the relay. It's actually a pretty clever electromagnetic switch. A small current flows through a coil, creates a magnetic field, and that field physically pulls a bigger switch closed. This lets you use a tiny, safe signal to control a huge, powerful motor. Simple enough, right?
Oh yeah, simple in theory. But in the real world, to create any kind of useful logic, something like, if this button is pressed and this guard is closed, then start the motor, you had to physically wire dozens, sometimes hundreds of these relays together. I mean, just look at this diagram. This is for a pretty simple process, and it already looks like a plate of spaghetti. It got complicated fast.
And honestly, this whole system was a total nightmare to work with. The wiring was incredibly complex and took forever to install. If just one of those hundreds of relays failed, finding it could take hours, even days. But the real killer was how inflexible it was. If you needed to change the process, even just a little bit, you had to shut the whole line down and physically rewire the entire panel. In manufacturing, downtime like that is absolute poison.
The industry was just desperate for a better way. And then, in the late 1960s, it finally arrived. It was an absolute game changer, the Programmable Logic Controller, or PLC.
And here it is. Just look at this thing. Compare this clean, organized module to that chaotic mess of wires we just saw. The PLC took all of that physical, hardwired logic and turned it into software. It replaced these giant room-sized cabinets of relays with one compact, tough, and, this is the key, programmable device.
So, what is a PLC? The best way to think about it is as a specialized, heavy-duty computer that's built to survive the harsh environment of a factory floor. Its entire job is to look at inputs from sensors, run a program that you wrote, and then control outputs to make things happen. It can handle everything from simple on-off stuff to really complex timing and counting operations. And the advantages were just massive, right out of the gate. Flexibility was the big one. Instead of rewiring, you just reprogrammed it on a computer. The response time was practically instant because it's all solid state, no moving parts to wear out or slow things down. The wiring became 100 times simpler, and troubleshooting was a breeze because the PLC could tell you what was wrong. It was a revolution in reliability.
Okay, so how does this industrial brain actually do its job? Let's kind of pop the hood and see how it connects to the factory around it.
So a typical PLC is modular. You've got your power supply, of course. Then you have the CPU, which is the brain that does all the thinking. And then you have these input and output modules, which everybody just calls I/O. These I/O modules are the most important part, really. They're the senses and the voice that connect the PLC's digital brain to the physical world of the factory.
And this table here frames the whole system perfectly. The PLC is definitely the brain, but it's totally useless by itself. It needs sensors, its eyes and ears, to tell it what's going on in the real world, like if a box is in the right spot. And it needs actuators, its muscles, like motors and pistons, to actually do things based on its decisions. The whole thing works together like a team.
Okay, so we keep saying we replaced physical wires with a program. So what does that program actually look like? How do you speak the PLC's language?
This right here is ladder logic. It's the most common language for programming PLCs. And the absolute genius of its design is that it was made to look exactly like those old relay wiring diagrams. See the two vertical lines? Those are the power rails. And the horizontal lines are the rungs of the ladder, where all the logic happens. This was so brilliant because it meant the electricians and technicians on the floor could pick it up almost instantly.
Let's look at the basic alphabet of this language. You've really only got two main types of contacts. A normally open contact, which is like a doorbell button. It's off until something pushes it. And then you have a normally closed contact, which is like an emergency stop button. It's always on, letting power through until you push it to break the circuit. That's pretty much it. You build all the complex logic from these simple pieces.
And this slide right here is the most important takeaway of this whole thing. What used to be a physical wire that you had to cut and screw into place is now just a line you draw on a software program. What used to take hours of downtime and a toolbox can now be changed in seconds with a laptop. This shift from solving the problem with hardware to solving it with software, that is the PLC revolution.
Let's walk through a super simple real-world example to see it in action. First, input. An operator walks up and presses a big green start button. The PLC's brain instantly sees that input. Second, logic. It runs the ladder logic program which says, hey, if that start button is on, then turn on the motor output. Third, output. The PLC sends a 24-volt signal out from its output module. And finally, action. That signal flips a motor starter and the conveyor belt starts moving. This whole cycle, input, logic, output, action, happens thousands of times a second. It's the heartbeat of the factory.
So, let's just recap the big story here. We started with these incredibly complex, inflexible, hardwired relay panels. Then we invented PLCs, these tough industrial computers that replaced all that physical wiring with software. This made our control systems flexible, super reliable, and way easier to fix. And the key that unlocked this whole transition was ladder logic, a programming language brilliantly designed for the people who actually use it on the factory floor.
You see, this jump from mechanical switches to programmable logic didn't just make factories better, it totally redefined what was even possible. It gave us machines that can think, adapt, and be completely changed with just a few keystrokes. So I'll leave you with this to think about. Now that you know how it works, if you could automate any process, what would you automate first?